Hello, we'll talk about another lesson in sectoral structures theory. Today we will talk about symmetric sectoral structures. So, a sectoral structure is symmetric if the standard form and the reverse are identical. So if we have a sectoral structure and we take its reverse and we get the same sequence of numbers, then that sectoral structure is symmetric. For example, if we have 3, 2, 3 subscript 8 and we take its reverse, we get the same sectoral structure, so therefore this is a symmetric sectoral structure. Or for example, 1, 2, 2, 1 subscript 6 is also symmetric. Also, every theta structure is symmetric since it's made up of only one part, and every xi structure is symmetric since all its parts are identical. Here we have two examples of sectoral structures that are symmetric. One of them is has n, that is an odd number, and one of them has an m here, which is an even number. And we will see that this is the key to distinguishing sectoral structures. So when we are studying sets of sectoral structures, as we progress, we will find that the key way to differentiate or categorize these sets is based on whether they are odd or even, and this further gives us a hint about some of the number theoretic applications of this theory. So here we have an is equal to 1 squared 3 1 squared subscript 7, and of course this is a sectoral structure with an odd number for its degree. And if we look at this sectoral structure, we will see that it is indeed symmetric, because if we take the reverse, we get the same sectoral structure. Now let's examine this a little bit more. We have the two delta joints here, and we notice that we can really draw a line of symmetry across this sectoral structure to divide it into two very special shapes. And this is a nice way to correlate, symmetry from the numbers into a geometric symmetry. And we notice that the curve is symmetric across this line as well. So we have these unique curves that are also symmetric over this line. Now, if we measure the curvilinear distance between the delta joint and this line of symmetry, we will find that it has a length of pi. And then if we measure the curvilinear distance from this point here, we're going to call it the midpoint, or m, to the other delta joint, it will also have a length or a distance of pi. Now, if we also draw a line segment between the delta joint and m, it will have the same length on both sides because they are symmetric. Now let's look at an example where the degree is even. In this case, the symmetry is a little bit different. So in this case, we have 3, 2, 2, 3 subscript 10. Notice that the symmetry really is not a mirror symmetry in this case, even though we know that this sequence is symmetric. In this case, it's more of a rotational symmetry. However, the distance between delta and the midpoint is also pi on both sides. And we notice that the midpoint in this case corresponds to a beta joint. So this is a very important property. And this will explain a lot of things that will emerge in the future. So when the degree of the structure is even and it is symmetric, then the midpoint is a beta joint, while in this case it's not a beta joint. It could be an alpha joint, or it could just be a point within the sectoral curve. Notice one more thing in this particular case, that the degree here is 7, which is odd, and also the number of parts is also odd. And here we have a degree which is 10, which is odd, and also the number of parts, which is even, and also the number of parts is even. Now always we have the theta structures are different, and because every theta structure is symmetric, and also the xi structures are a little bit different because every xi structure is symmetric. Now let's look at a special type of sets, or partial sets really, which are the symmetric sectoral sets. So the reason we try to avoid calling them subsets is because we want to think of them as their own sets, but they are subsets of the complete sectoral set. So for example, if we look at ST1, it has only one sectoral structure, which is theta 1. And therefore, all these structures in this case are symmetric. So we will call these T omega 1. So T omega will correspond to the symmetric sectoral sets. So T omega 1 will be made up of theta 1. So it really includes the entire set. And then T omega 2 will include theta 2 and xi 2, which are the two elements of ST2. So again, in this case, all the elements are included. Now, once we reach ST3, things start getting different. So ST3 is made up of theta 3, xi 3, and the sectoral structure 2, 1, subscript 3. In this case, only 2 of the structures are symmetric. So we will say T omega 3 is made up of theta 3 and xi 3. Now we will also define a new function, which is the omega function in this case. So if we say we've seen the mean function prior, we're going to revisit it later, but we will say omega 1 or omega of 1 is equal to the size of the sectoral set T omega 1. In this case, that's 1. Omega of 2 is equal to 2. Omega of 3 is the size of the symmetric set T omega 3. So it is the set of all symmetric structures of degree 3. And in this case, it also equals to 2. Let's look at ST4. ST4 is made up of theta 4, xi 4, 2 squared 4, 3 1 subscript 4, 2 1 squared subscript 4, 1 2 1 subscript 4. So what are the symmetric structures here? We have the theta 4, we have the xi 4, we have the 2 squared subscript 4, and 1 2 1 subscript 4. So we have 4 symmetric sectoral structures. So we will say T omega 4 is equal to theta 4, xi 4, 2 squared 4, 1 2 1 subscript 4. So we have 4 symmetric sectoral structures, and we will say that omega of 4 is equal to 4. Now for ST5, I'm not going to write all the elements, but we're just going to look at the T omega 5, so the symmetric sectoral structures of degree 5. And these are theta 5, xi 5, 1, 3, 1 subscript 5, and 2, 1, 2 subscript 5. So there's really only 4 sectoral structures of degree 5 that are symmetric. So we will say that omega of 5 is equal to 4. So notice if we continue doing this, the pattern becomes very clear. It's 1, 2, 2, 4, 4, and if we continue more, it will be 8, 8, and so on. And we can go into the combinatoric proof in another lesson of why this really is the pattern and it's going to hold. But to simplify it, we're going to say omega of n is equal to 2 to the power of n over 2 if n is even, and it is equal to 2 to the power of n minus 1 over 2 if n is odd. So we can simplify it into this expression, into a single expression right here. And this is going to be at the core of a lot of our study of why we're going to see a lot of differences between even and odd degrees for sectoral structures. But this is at the very core of some of the numerical patterns that will emerge. It's because omega of n is different depending on whether n is even or n is odd. And at its very core, it's a geometric observation. Now going back to our prior lesson where we looked at fitting in and belonging. So we're gonna look at an interesting pattern. Notice here the fitting in sign is reversed because I wanted to point in the direction of the fitting in, so the epsilon signs are reversed here. So let's assume we have a symmetric sectoral set T omega n, which is a subset of STn. And let's say we have another symmetric sectoral set TNM, which is a subset of STM. Now, if we have the following relation, STM is or fits in to STN. So for example, if we have ST2 and ST4 or ST6, then we know that ST2 fits in ST4 and ST6. So if that is the case, then we can say that T omega m fits in T omega n. So the symmetric sectoral set of degree m fits in the symmetric sectoral set of degree n. And try to think about what that means geometrically. And we can also say, of course, by default, that T and M fits in ST n. So therefore, just a reminder, what we're saying here is that if we have two symmetric sectoral sets of degree n and m, such that, another way to say this is such that m is a factor of n, then the symmetric sectoral set T omega m fits into the symmetric sectoral set T omega n. And this is gonna have some interesting applications if we think of it, and it can also help us explain this emerging pattern. Thank you.